Okay, so I'm going to go over the last few sections of this chapter 5, and this is about equilibrium, 3 dimensions, and we're going to learn about the type of constraints that we can encounter, some of them, not all really, that we encounter in solving equilibrium of systems of bodies in 3 dimensions. So we can find cables. Uh, the These could be only one unknown's tension in the cable, which cannot be only away from the body and in the direction of the cable. Cables cannot take compression. And then we can have um, smooth surface or roller contact without friction, and then there's a normal force once we release the body and has a direction of the from the contact point to the center of curvature or to the center of the roller. And then a ball joint, ball and socket joint. um, Here all 3 rotations are permitted, but none of the translation. So we have 3 reaction forces, 3 unknowns that are introduced when removing or releasing a body from a ball and socket joint. We have single journal bearing. This is like a cylindrical joint, so you can slide and rotate about its own axis. This rod relative to the bearing. And we're going to introduce, because translation is not possible, transverse to the rod. We're going to introduce 2 forces, and since rotation is likewise not permitted on axis transverse to the rod, we have moments. There's no force and no moment, so that's why out of 6, only 4 unknowns are listed here. So no force in the direction of sliding, no moment about the axis of the rod. We're moving here to single journal bearing with a square shaft. This is a prismatic joint, sliding joint, that is. We have 5 unknowns. So sliding is permitted, but no rotation. So we will see 2 reaction forces transverse to the um, prismatic body, and then or rod, and then you're going to see all 3 moments about the 3 axes. Single thrust bearing, that's a pin joint, really is the same as single smooth pin and hinge. So here we have rotation about the axis of the rod or the hinge or the pin permitted. So we see only a force, and then force, and then moments are shown, because rotation is not possible, transverse to the axis of the pin or the bearing. Okay, so we'll have 5 unknown reactions. That is 3 forces and 2 moments, so 5 unknowns for all these 3 cases. And then we have a fixed support where the all degrees of freedom, 6 in total, are suppressed. So we're going to see 6 forces and 3 forces and 3 moments, showing the effect of the surroundings upon the body. Some examples, everyday life examples, photographs of the author, and then free body diagrams. So we need to draw free body diagrams, choose proper reference frames, and define the um, effect of the environment or the surrounding bodies, interacting bodies, upon the one that we want to analyze. So some examples here with cylindrical joints, I call them, or journal bearings without thrust, possibility of thrust loading. So we have two unknown forces, two more and two more, and it doesn't show the moments really. So the free body diagram is represented here in this figure. And then if we have a cable, you introduce the tension on the cable. This is like a hinge, so we have no moment about the y-axis as shown, all forces shown, and no moments about the transverse axis z and x, that is. Okay. So to solve for the unknown forces and moments introduced when drawing the free body diagram, we can write the force and moment equations in 3 dimensions. So sum of forces vector, sum of moment of some point about some point O, conveniently selected. And these are equivalent or can be expanded into 3 scalar equations for forces, 3 scalar equations for moments, so 6 scalar equations total, so we can handle at most 6 unknown reaction forces and moments. There is the possibility of having too many constraints over the number of equations it can write. So these are the redundant constraints in statically indeterminate systems, meaning that we have more unknown reaction forces and moments then we can write equations. So here's an example, although this is two-dimensional. So we have a fixed end and 2 rolling supports. Rolling supports are produce forces, reaction forces that are perpendicular to the line of contact. And then at the support, we have 2 forces and a moment. So total 3 here, 3, 4, 5. While in 2 dimensions, we cannot write more than 3 independent equilibrium equations. So too many unknowns for the equation you can write. This is statically indeterminate system. Some constraints are redundant. We can actually remove these 2 and still have or the body will be in equilibrium. The systems like these are encountered in practice, are called supported cantilever. In strength of materials, mechanics of materials, we're going to study them. But in order to find the reactions of the supports, we need to account for the deflection of this long body, the beam. Here's another example where you have a fixed end and a sliding cylindrical joint that is journal bearing without thrust. So we have 6 unknowns at this support and then 2 more here, so 6, 8, but we can write only so 8 unknowns, but we cannot write only 6 equilibrium equations, insufficient to solve for the unknowns. And then we can have improper constraints. Gives here an example. So there's the pin end, and then we have a rolling contact here. If we analyze the balance of force in the horizontal direction, you cannot tell how AX and FB are going to share the load caused by horizontal component of force P. In the vertical direction, it's clear that we have AY equals the vertical component of load P. And here it shows a L-shaped piece or bar that is ball socketed, jointed at A and B. This is going to actually rotate about the axis connected to these 2 ball joints. And so it won't remain in this configuration. It will deflect its hold to reason. So this is going to just sag, and the L bone will be in the lowermost position, assuming that this load P follows. Okay. And then some other examples. So these are in unstable systems. We cannot locate the beam really. So the horizontal component of the force causes this whole beam to move to the right. Again, they are rolling contact, and there's no means to resist the horizontal component, this force P. Okay, we have here a system with parallel cables, and the force is perpendicular to these cables will cause the unit to deflect, in parallel, like assuming these are equal length. Okay, so yeah, unstable equilibrium for this kind of loading. And here we have a set of 3 links hinged at A and B, and also hinged to the ground. And there is with this loading transverse, we're going to see the slight tendency for this to sag, and equilibrium of link AB is not going to be maintained for this initial configuration. All right, so some part of these important points says stable body requires that the line of action of the reaction force not intersect the common axes, are not parallel to one another. So parallel or intersecting cases, which result in unstable equilibrium, or we cannot maintain equilibrium in configuration of the system with the constraint provided. So some inspection is required to document or to identify these anomalies, or rather systems cannot be analyzed for equilibrium because the equilibrium is not sufficient or satisfied. Some example problem, recommend you to go over them. And things that we learned in early chapters, like resultant of systems of force and moments in 3 dimensions, are useful here. And then some more examples. And then what do we have? We have a summary of findings from this chapter 5. So what type of reactions for various supports in 2 dimensions, and the equilibrium. I'm sorry, I'm pointing to the wrong. And the equilibrium equation, 3 of them in 2 dimensions. In 3 dimensions, the most common of the constraints, and then the maximum of 6 scalar equation you can write to solve for the unknown reactions. Okay, and then stability and determinacy. So too many reactions over the number of equations that can be written, or unbalance of forces or moments due to the insufficient constraints in the system. Okay, so yeah, this is it. I'm going to stop here and post the recording. Thank you.